Welcome to my video math review series for Calculus 3, otherwise known as multivariable calculus, or if you're a Georgia Tech student, it'll be Math 2551. I have tutored this course for over 6 semesters now, and I'm going to use this break due to the coronavirus to catalog all of the experience that I've gained in helping students with these math topics. I'll be using some of the worksheets that I've created over the last 6 semesters just to kind of guide us through. Some of them I'll ask you to work on your own in between watching the videos and to feel free to pause at any time to work through some of these problems before we do them together. These will not be scripted at all. I'm just going to improv it as I go. So they're kind of going to be some performance art pieces. So we'll see how they turn out. But with that in mind, let's jump straight into chapter 15 and talk about iterated integrals. So if we look at the title, iterated integration just means integration that you do more than one time. So it's going to be repeated, or you'll see it's like nested integration. So to begin talking about what double, triple, iterated integrals look like, I want to start by drawing some comparisons between single integrals and double integrals, that first step into iterated integration. So the ways I want to look at integration is in 3 different perspectives. One, the form, the syntax, the mathematical syntax we use to write them, the graph of what's going on, as well as a statement about the interpretation of what we just found with an integral. So starting with single integration, the form is something we've seen all the time. So you're very used to seeing this from Calculus 1 and 2. It's a single integral of a variable with a function with one independent variable, dx, right? So f of x dx, one variable function with one variable of integration. And then if it's a definite integral, then that will be over an interval a to b, right? And these are, you may have never written it out explicitly this way, but these are x values. These are x equals a to x equals b, right? And that's because you're integrating with respect to x in that case. So the graph of what's going on here for a single variable function being integrated is you have your axes, x and y. You're on the xy plane. Here's our function f of x. And then if we're treating this like a definite integral on the interval a to b, right? And these are x values, so they are on the x-axis. Right? And then we're very used to understanding the interpretation of the integral of a single variable function being the area under the curve, right? So that's going to give us this area, right? And we've had experience approximating it with a Riemann sum. We've learned different integration techniques, and all those are going to be conserved even for functions of more than one variable. And now let's look at the interpretation here of what's going on. So if I were to write out a sentence that kind of summarized this graph and the output of it, what we've gotten, it would be something along the lines of the signed area under the curve f of x over a given interval. So let's break apart the important words in that sentence. So it's the signed area, right? And this signed area just means that in general, in the real world, we're used to thinking of area as being only a positive value. You can't in general have negative area, but when we're talking about integration and the interpretation of it, if this function dips below the x-axis, then this counts as negative area, right? So we have the signed area under the curve f of x, right? So if it's a function of one variable, then you have a curve over a given interval, and that's usually written as like a to b. Excuse me. So those are the important parts in that sentence. So that was a review of single variable integration. Now let's do double integrals. So in double integrals, no longer do you just have one integral, you actually have two. So you have two integrals, no longer a function of one variable, but we are integrating a multivariable function. And because you're doing more than one variable, now you can't just integrate with respect to x. You have to actually integrate with respect to x and respect to y. So now we have the double integral of f of xy dx dy. So these are kind of nested. You could imagine putting some brackets in here and treating this inner integral as one, evaluating it, and then moving on to the outer integral. And just like the other one, if this is a definite integral, then you're actually going to have 4 boundary conditions. So no longer is it just bound by a to b, but it could be bound from a to b and then c to d. So you have 4 different bounds that bound your integral. Just as another note, this dx dy here, in general, is written as dA. And we'll explore why it's written as dA in a second, but you can kind of combine dx dy, just write it as dA. So now let's do a graph. Let's draw a little picture of what's going on here. So now that we're doing multivariable functions, we're not just on the xy plane anymore, but we have to draw 3-dimensional axes. So we have x, y, and now we have the z-axis. So our function f of xy, remember, validate that if a function has 2 variables, then in general it's going to be not a curve on the xy plane, but rather a surface in 3D that takes in the independent ordered pair x and y and outputs a height, right? So you're going to be graphing some kind of like surface that looks something like this. This is just my generic surface. We'll call this f of xy. Okay, so we drew our surface, and now we need to draw our boundary conditions, the bounds on the integral, so these guys. And now, instead of just having an interval of integration, you actually have a region of integration. So in this case, the x variables go from a to b. So in the x-axis, we're going to be going from some a to some b, and in the y direction, we're going to be going from some c to d. Right, so in the y direction, we'll be going from c to d. And so the intersection of all these conditions actually traces out a really nice region of integration that in this case would look something like this. And in general, we call those R. Right? So this region that we're integrating is R. And just like in single variable calculus, integrating a function of one variable gave you the area under the curve, we'll be finding a similar quantity. Everything's just bumped up a single dimension, in this case for double integrals. So before we draw any more on the graph, I want to do the interpretation. So let's write an interpretation in purple. So we're almost going to use the exact same sentence structure from our single variable integral, but we're going to adjust all of the underlined words to make them appropriate for a higher dimensional function. So in this case, we don't have the signed area under the curve. What is one dimensional higher than area? So area is like x and y. It's a 2-dimensional idea. Now we have the signed volume. Okay, so we got the signed volume under the curve f of x. So no longer does f of xy give you a curve, but we call this a surface. So this is the signed volume under the surface. All right, now f of xy, 2 variables, over a given interval a to b. No longer are we integrating over an interval, we're actually integrating over this region R. So it's the signed volume under the surface f of xy over the region given by R, right? We always get R from the bounds of the integral, right? This right here is where we got that region of integration. So you can see the comparison. The sentence structure is exactly the same. The signed area under the curve, now it's the signed volume under the surface, no longer over an interval, but now over a region. So everything is just 1 dimensional higher. And you can actually draw this. What the volume over the region R under the surface looks like is you're really finding the volume of this. It would, in this case, kind of look like this rectangular prism with kind of this curved top. It would have an irregular top. So let's see, it would kind of look something like this. This is going to really test the ability of my drawing skills. But you're finding this volume contained in here. So it would be this volume right in there. So in this case, it's just a rectangular prism with an irregular top that's defined by the function xy. Okay, now let's take a look at this important idea as well. This is one of the very important theorems in double integration, or really any iterated integrals, and that's Fubini's theorem. And Fubini's theorem is really talking about the order of integration. And we've never explored this before because in single variable integrals, you only had one variable of integration, so there was no multiple ways to do it. But now that we're doing double integrals, you have two options. You can do dx, dy, or what Fubini's theorem says is a double integral dx dy is equivalent to doing it in the order dy dx. So the order of integration doesn't matter. And that's why we can generally write the variables of integration as just dA. And dA encapsulates both the order dx dy and dy dx. Now that's going to be important to remember because oftentimes when you're setting up these integrals to solve and to evaluate, it is either one, easier to do it in one order than the other. So it's easier to evaluate it, say, in the order dx dy as opposed to dy dx. Or in some instances, it can be impossible to write a single integral for one of the orders or the other. So you'll have to pick dx dy or dy dx. And we'll look at some cases where it's beneficial to pick one or the other and the things you should look out for when you're choosing an order of integration. So to begin, let's just do an easy example of just evaluating an integral, a double integral that's already been given to you. So this is a pretty straightforward example. It's just been handed to you really nicely. It's already set up. So it's a double integral. This right here is the function. This is f of xy. All right, so this is that surface. This is that surface that lives above the xy plane. And then these here, 0 to 4 and 1 to 2, those are your bounds for the region of integration. So these tell you about R, that region on the xy plane that you're integrating over. And you know what type of variables these are, because these variables must match up with the order of integration. What I mean is that if you're doing dy first, these bounds must match up with that variable. So these are really y variables. So this is from y equals 0 to y equals 4. And similarly, these have to be x bounds. So this is from x equals 1 to x equals 2. So you don't ever have to write it this way, but sometimes it's helpful, especially when you're beginning, just to write the variables that go along with those numbers, just so you know what axes that you're writing those bounds for. So let's evaluate this integral real quick. So just like when we were doing partial differentiation and you're differentiating with respect to one variable, now we're just integrating with respect to one variable of the other, and you know which one you're doing based off of the order of integration at the end. So we know that we're going to start with y, so we're going to integrate with respect to y first, and so in this case we'll treat x just like a regular constant, so we'll get the integral of 2xy is going to become x y squared from 1 to 2. Right, now that's going to be evaluated from 0 to 4 dx. So all I did here was I evaluated this inner integral. The inner integral, evaluated it here. So this is now a single integral that we have to do. So we'll get from 1 to 2. That'll become 16x dx. And now it's just turned into a regular single variable integral. And so that'll become, I believe it's 8x squared, evaluated from 1 to 2, and that is 24. So we got 24, and just to remind you, the interpretation of this is that on this region R from 0 to 4 and 1 to 2, so that's some region on the xy plane, under this surface 2xy, the volume, the amount of space it contains, is equal to 24 units, whatever units that this problem was in. Okay. Now let's just look at sketching some regions of integration. So in this case, we're not even given a function to integrate. All we're doing is from bounds on our integral, let's try to sketch the region that we're integrating over. So this wasn't really a skill we practiced in Calculus 1 because it doesn't really exist. That would be just like interval sketching, and I think everyone can sketch like from 0 to 1 or from 3 to 5 or something. But now we're going to be looking at the different regions, right? We're just sketching this region R, right? This is what the problem's asking us to do, given these bounds, A to B and C to D. So let's look at this problem again. So this is saying, sketch the described region of integration where the x variables go from 0 to 1 and the y variables go from e to the x to e. So this is interesting. Now, because we have double integration, some of our bounds can be functions of other variables, right? And that looks really scary, but you'll see that we can sketch it relatively easily. So let's get some axes set up. Right, and because we're doing just the region of integration, I just need to sketch the xy plane because the region R lives in 2D. It is a two-dimensional idea. It lives on the xy plane. So I just sketched this. Let me pick a color. We'll do yellow. So for our x variables, x will go from 0 to 1. Here's from 0 to 1. And let's see, y goes from e to e to the x. So let's see, e to the x would be this function here. Here's y, here's e to the x. And then y equals e would be just a straight line, right? At a height of y equals e, which would occur, oh, that would actually occur at 1. So that's like something there. Right, because when e to the x is evaluated at 1, then it's just the value e, right? So our region of integration in this case is going to be this. So this irregular wedge-shaped region, that is R. That's our region of integration. And then if you were given some function, it would live like above my iPad right now. It would be in the third dimension, and you would find the volume between this wedge-shaped region and the surface that lives above it. Okay, so now we're going to look at doing the other way around. So now, instead of being given limits of integration and drawing the region, we're given a sketch of R. Here's our region of integration. And now reverse engineer what the bounds must have been in order to produce a region that looks like this. So what I'm going to do is, in general, I would start by writing the equations for all of the boundary conditions, but it looks like they were already given. So this curve here, right, you'll recognize as y equals x cubed, and then this horizontal line running across, that's just y equals 8. And then it might be helpful to find what this intersection point is here, so you can get your x bounds as well. So we know x will go from 0 here to, where would that intersect? That would intersect at the point 3. That would be x equals 3. So we can write a double integral of some generic function that we don't know yet. And now let's pick an order of integration. We can do either dy dx or dx dy. Here's a tip. Because these are already solved in the form y equals a function of x, like y equals x cubed, it's often easier to do dy first. So in this case, we're going to do dy first. So we'll do dy, oops, and then dx. So in this case, the y variables will go, so the lower y bound, in this case, is actually y equals x cubed. So this will be from x cubed up to y equals 8. And that's true across the entire domain of the region, right? You're going from this lower curve, which is x cubed, up to the upper curve, which is 8. So from x cubed to 8, and then the x bounds would be pretty easy. Those just go all the way from 0 to 3. So it'll be from 0 to 3. Okay, cool. And now let's reach into Fubini's theorem. If you remember, Fubini's theorem said that if we did dy dx, we can equivalently write it in the form dx dy. So let's rearrange this to do dx dy as well. So let me set up our template. So now we need to go in the x direction first. So I'm going to erase all this. So look, if we're going in the x direction first, we're starting here, and we're first going across the x direction. So it looks like this. So it looks like across the entire domain of the region, we start at x equals 0, right? So here's x equals 0, and we're going to this curve. So it ends at this curve, but it's written in the form y equals something, right? And remember, if we're doing dx first, then these must be in the form x equals some bound. So all we have to do is resolve this in terms of x. So that's pretty easy. We can do x equals the cubed root of y. So we go from left to right. It'll be from x equals 0 to x equals the cubed root of y. And then in the y direction, it looks like we just go from 0 to 8. So that's pretty easy. That'll be from y equals 0 to 8. So our outer bounds are 0 to 8. Now the reason I had to resolve this in terms of x equals something is that if I didn't, we would have had a variable bound as the outer integral here. We would have had something in the form of y equals x cubed on the outer integral. And an important idea in double integration is that the bounds on the outer integral, whichever one is the outermost integral, must always be, I'll make a note about this. So the bounds on the outer integral must always be between constants. And the reason for that is that when you go to evaluate this final integral, right, you'll evaluate the inner one and then the outer one. When you do the fundamental theorem of calculus and you plug in the top minus plug in the bottom here, if you have variables, then you're not going to get a final answer. Your final answer won't be numeric. It'll be in terms of one of the variables that you've already integrated with respect to. So you need to make sure to remember that the outer integral is always between two constants, and we did that pretty easily by ensuring that we captured this function in the x variable by just solving it in terms of x. I'll leave number 10 for you to do on your own as practice, and we'll go on to this next one. So finding region of integration and double integrals. So now we're going to sketch the region of integration and evaluate the integral. So this is a two-part question. So number 1, sketch the region of integration. So remember, the region of integration has to do with the bounds on your integral. So all we're doing right now is we're looking at this. We're not even paying attention to the function on the inside. So we can ignore whatever function's in here because that's the surface that lives above the region of integration. So let's just look at from y equals 0 to y equals x. And then we have from x equals 0 to x equals pi. Okay, let's sketch this out. So we're drawing a region of integration, so we just are on the xy plane. And we know that in the y direction, we're going from 0 to x. So from y equals 0 to y equals x. And we know that this function y equals x, that's our 45-degree line. So I'll just put that in there. There's y equals x. And then we're going from x equals 0. So here's x equals 0 to x equals pi. And so pi is just a number that's going to be, that'll live around here. That's like pi. You can see that's 3.14 or something. And then that creates this triangular region right here. And if you wanted to know the height at which that occurs, because you're on the 45-degree line, y equals x, this intersection here actually occurs at the point that would be pi pi. So here's our, here's our region of integration for number 19. I'll let you do the evaluation on your own. So I'll take that out so you can evaluate this function. Let's just set up this one as well, because the setup for these problems is really the most important step. So let's get some more axes in here. Here's x and y. Okay, Similarly, we're just drawing the region of integration, so it doesn't matter what the function is in the middle because that function lives in 3D. This is y equals 0 to y equals sine of x. So that is between a constant and a function. So let's draw in, I'll just draw one period of the function y equals sine of x. All right, so that'll be sine does something like that. And then just to label a couple of these points, right? We know that this will be a height of 1. This occurs at pi halves. This is pi. This will be 3 pi halves, and so on. And then for the x variable, x is bounded by x equals 0 and x equals pi. So x will go from 0 all the way to pi. So that carves out this region right here. So by combining different functions and constants in the x and y directions, you can actually trace out some pretty interesting regions of integration. And then if you were to add in this function, right, so this is f of x, in this case just equals y, that would be some three-dimensional function that lives above, in the third dimension, above the plane, above the region R. And then you can take some time on your own to evaluate that on later. Okay, fantastic. Let's keep moving on. A word problem. So this is our first real-world word problem that we've encountered, and that'll be to find the volume, right? That's what we talked about. Double integrals in general give you volume of the solid whose base is the region, right? We've been sketching those regions are bounded by the parabola y equals 4 minus x squared. So here's one bound, and the line y equals 3x, while the top of the solid is bounded by the plane z equals x plus 4. Let's dissect some of this information real quick. So we've been trying to distinguish between the region R on the xy plane and the surface or the function f that lives above the xy plane. So we have to dissect which of these equations and which of these boundaries are talking about which part. So when we talk about the region on the xy plane is bounded by this parabola and this line. So all of this goes with R. And then we also have the top of the solid, right? The top of the solid is like this function. That's the function f of x. So the top of the solid is given by the plane z equals x plus 4. So in that case, that is our f of xy, right? And we know that f of xy is just another way of writing z. Just like f of x is the same as writing y, right? F of xy is equal to your dependent variable. In this case, it's z. So here is our f of xy equation. So what did it want us to do again? So find the volume of the solid whose base is that, and the top is this function. So that means we're writing a double integral where our function that goes in the middle is our x plus 4. So I'll just put it in some brackets so we don't lose it. It'll contain it in there. And then we'll pick dA, right? So with any generic order of integration. Now we have to deal with the region. The region lives on the integrals. Those are the bounds of the integral. And it looks like it's bounded in the y direction by the parabola y equals 4 minus x squared and the line y equals 3x. So my advice whenever you're working these double integral problems is always sketch out the region of integration. So I'm going to take a second to come over here and let's just sketch R. So let me get some axes set up. So we're just going to sketch the region just to get our bounds in order. So it looks like we have the parabola y equals 4 minus x squared, which would be something that looks like 4. All right, something like that. And the line y equals 3x. So that's going to be, oops. So here's y equals 3x, and here's y equals 4 minus x squared. So you have that downward facing parabola and your just straight line y equals 3x. And so our region here is something that looks like well, let's take a look at this a little bit closer. I think I messed up here somewhere. Oh, I didn't draw the region big enough. That's what it is. Okay, I need some wider axes. That's what I was missing. So let's draw a bigger chunk of this. Here we go. So here's that y equals 4 minus x squared. And then we'll get in this 3x. Okay, so our region here is actually this guy. So it doesn't just live in quadrant 1, it actually extends into 3 of the quadrants. So here's R. And now we just need to find these points of intersection. So this occurs, where does 3x equal 4 minus x squared? That would occur at the point x equals 1. And I believe this one, you can solve for this intersection point to be, I believe that's going to be -4. So here's our region. We have y bounds and x bounds, and now we just need to put those on here. So like I said, because our y bounds are functions in terms of x, they should go first, which means we know our order of integration will be dy, then dx. So let's get the y bounds will go from this line y equals 3x to the parabola 4 minus x squared, right? And that's true across the entire domain, right? So when we're going in the y direction first, we're going from 3x to 4 minus x squared. And then in the x direction, we're just going from -4 to +1. Beautiful. And that looks really nice. When you put these functions here on the inner integral, right, when you plug them in after you evaluate, then you're going to have just variables of x in your function. And that works out perfectly because the next step will be to integrate with respect to x. That's why it's important to make sure that that in fact these are bounds in the form y equals something, right? Because it sets up your variables to be continuous throughout the entire problem. Okay, I'll let you solve this on your own. So solve this on your own. But I will give you a little guidance that you should be looking for the answer. I'll put this in spicy red. So the answer will come out to be 625 over 12. So if you get that as your answer, then you know you did it right. Okay, so we've been talking a lot about that double integrals are used to find volume, but there is a condition in which you can use double integration to find area of your region of integration. So if you have an irregular shape or an irregular region of integration, you can set up a double integral that will find that area if, and this is the big if the function you integrate right, that's your f of xy, is equal to 1. So if f of xy just equals 1, then you know that that will give you the area of the region of integration. So this is actually a general idea. The general idea is that whenever you're integrating 1, so here's a single variable example. If you integrate a function that's just 1, then it tells you something about the interval or the region of integration, something about the bounds, right? So if you were to solve this, right, you would get, that would just be x evaluated from 3 to 1, which is 2. So 2 is your length of the interval. Right, so in single variable, you don't get the area of the region. By integrating 1, you get the length of the interval. Similarly, in multivariable, if you have something like this, from 0 to 2 and 0 to 3 of 1, right, that will just end up being 6, which is the area of the region of integration, because your R for this case will actually look like, that'll be from x equals 0 to 2 and y from 0 to 3, right? That's this box here, and that area is equal to 6. So again, if you're integrating a function 1, then it will not be the volume of some surface over an interval or over a region, but it's actually just the area of the region. And then the last idea I want to talk about is the average value of a multivariable function. So we can draw a comparison again to our single variable examples. So remember, in single variable calculus, if you wanted to find the average height of a function, that's the same as finding the average value of a function. That was equal to, so you did the integral from a to b, but you had to divide it by, and if you remember, it was b minus a. So it's 1 over b minus a times the integral from a to b of your function. And really what this is doing is it's taking the value of the integral and dividing it by the length of your region. So that's divided by the length of interval. So we're doing the exact same thing in multivariable as well. So now let's do our multivariable example. So now for 2 variables, now you'll have a double integral from a to b and c to d of a function of 2 variables, dA. And now, what do you think? Instead of dividing by the length of the interval, you're actually going to be dividing by the area of the region. So it's the area of R. So the average value of a 2-variable function is equal to 1 over the area of the region of integration times the double integral. Now, another way to write this is, right, so the average value or the average, this could be the average height, right, on the z-axis, the z height is equal to, if we pull out this that we just learned, the double integrals can be used to find the areas of regions if your function is equal to 1. So in this case, we could set this up as 1 over the double integral of 1, right? And confirm that this would actually give you the area of R. This is equivalent to 1 over the area of R. Similarly, times the exact same double integral. So that will give you the average value, the average height, the average, this is z height. Let me get that a little bit farther over. So that'll be the average z height of your multivariable function. Oh, let me see if I can take advantage of the straightening tool. There we go. Beautiful. Okay, so that is the average value of a multivariable function. Double integrals can be used to find the areas of the region if you integrate one, and then we have a lot of practice with setting up these regions of integration from given bounds or using given bounds to sketch the region of integration. Okay, I will upload those notes online where you can access them, and let me know if you have any questions. Okay, thank you.